All right, this is RSA, Ravesh Shamir Alderman. And there's actually, if you read that crypto book, which none of you in here have, I don't think, it's amazing to tell you all about this. Still used today. Still used today. And let's figure out why we can't advance. There we go. Okay. Ravesh Shamir Alderman, 1978, based on factoring large numbers. Very large numbers. Now, I'm going to tell you up front, because someone mentioned it last semester, we're not using large numbers in here. We're using very small numbers just so we can do it. Okay? People say, I can't do this time if the numbers aren't 200-bit. You know what? Just do the small numbers just for practice, okay?
Complain about being given the small numbers.
Yeah. Well, actually, some of them are larger this year because of that.
Well, I do believe that's also the same as don't complain about him extending the deadline.
Yeah. Oh, I had a student complain about me extending the deadline.
No, we got that story in here.
Still complete. Okay. Best factoring algorithms are exponential. In other words, it's tougher. Obviously, exponential numbers are crazy bigger, so there's no known weaknesses. So, if you were to see a test question that said, what weaknesses are there for RSA, you would say, none. No known weaknesses. Now, there is a weakness that's been reported, but it's hardware related. So, you know, one of these RSA encrypted flash drives, there was a hardware problem that caused it to break, but it's not the algorithm's problem. So here's how it works. Choose a large n, which is equal to p times q, which are prime numbers. So take two prime numbers, multiply them together, you get n. Easy enough so far? Very, very simple so far. Then choose E that is relatively prime to the totient of n, which is equal to p minus 1 times q minus 1. So remember, p times q is n. P minus 1 times q minus 1 is the totient of n. It just is. Okay? Go with it. Just is. Then D. D is equal to the multiplicative inverse of E mod totient of n, which we'll see how to do in a minute. And you'll see where all this becomes important. Okay. Now, is RSA, what do you think? Is it public key or a private key?
Public.
It is. It's public key. So we need an encryption key and a modulus, and a decryption key and a modulus. Okay. So we encrypt something. So we take our plain text, encrypt it with E mod n. That becomes our ciphertext. Then we take the ciphertext, decrypt with D mod n, and get our plain text again. So there's a relationship between the two keys. And as long as you don't mix them up, you're good. It's not a problem. D and E, it really doesn't matter which one you use for what, as long as you do not mix them up. Okay. Totient. What the totient is. Okay, the totient function, also known as Euler's totient function, is defined as the number of positive integers less than or equal to n that are relatively prime to it, but does not contain any factors in common with it. Okay? Now, so there's 8 toatives relatively prime to 24. Okay? So the totient of n would be 8. Do not do it this way for the assignment. I added that because it's last semester, sure enough. Okay, how do you calculate totient of n? Does anyone remember? P minus 1 times q minus 1? P minus 1 times q minus 1 is the totient of n. Don't do it the other way. For my assignment, do it the way I told you. I just added this so you kind of get an idea where the totient of n comes from. But do it the way I'm telling you. Okay? So I did that. I added the red today just so y'all wouldn't mess that one. Alright, so the mathematics is the totient function, number of positive integers less than n that are relatively prime to n. We know that. If p is prime, then the totient of p is p minus 1. If n is p times q, and p and q are prime, then the totient of n is the totient of p times the totient of q, and so on and so forth. Basically, p times q is n, p minus 1 times q minus 1 is totient of n. That's all there is to it. Okay? If you can remember that, you are golden. That's all you need. So the main result, if you encrypt something with an encryption, basically it works out. Encrypt with an encryption key, decrypt with a decryption key, but you do not need to remember the math behind this. So math for this is incredibly simple. Much, much easier than any of the other ones we've done. Here it is. So, we start with 3 and 11. And it's P times Q, 33. So far so good? Really, really, really super basic math. The totient of n is P minus 1 times Q minus 1. So it ends up being 2 times 10. It's 3 minus 1 times 11 minus 1. 2 times 10, 20. Choose E of 13. I will give you E. I provide you with E. Just needs to be relatively prime to 20, which it is. That's a prime number relative close to it. But for the assignments, use the numbers I give you. Don't say, well, that's not relatively prime. Yeah, it's to go with the numbers I give you, okay? Find D such that E times D mod n is approximately equal to 1. Happens to be 17 in this case, which I'll show you how to calculate here in a minute. So our public key will then be E and N, and our private key will be D and N. So if I give you 7, you go 7 to the E, mod 33, gives us 13. Then 13 raised to the D, mod 33 gives us 7. That's all there is. That's all the math. Very, 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 very simple. Haven't told you how to get D yet. It's going to look very familiar. Okay? Calculate D. To compute the value of D, use the extended Euclidean algorithm, also known as modular inversion. But it's much easier than that. Okay? Which I'll get to in a minute. So, for RSA, choose prime numbers P and Q, 100 digits long each. But go with the numbers I gave you. Calculate N, which will be 200 digits for 512-bit, 1024-bit, or so on and so forth. Choose D that's relatively prime. We talked about that. Compute D. We know that. And we know what our public and private keys are. And once we know what E and D and N are, we can really throw away everything else. We don't need it anymore. Because we use P and Q to calculate N and the totient of N. So we really don't need them anymore. Okay. Congruent. Corresponding or congruous. It says coinciding exactly with superimposed or congruent triangles, or, and the one that really pertains to us, or relating to two numbers that have the same remainder when divided by a third number. For instance, 11 and 26 are congruent when the modulus is 5. Again, it's not important you know this. It's just that it was in the definition before, so I put that in there for you. So assume that P is 3 and Q is 11, which the answer we already showed you. This is the exact way you'll see the assignment. It says, if the public key coefficient E is 13, which I will always give you that, compute D. So we calculate N, we calculate the totient of N. Then we need to figure out what D is. Here's how you do D, right there. Does that look familiar at all? Remember we did that multiple times? I told you you're going to have it. Here's where you need it. So, instead of, it was what, N and W? NWC? Now you're using the totient of N, E, and comparisons. So remember, in this example here, we had 3 and 11, so the totient of N is 2 times 10, so we get 20. E is 13, so we have 20 and 13. Go all the way down till they match. And again, the E column, wherever they match on the E column, is the comparison number you use. So D 17. Did you write a program to do this?
Script for the comparison method.
Nice. Nice. You can use it. It'll be perfect. So I told you, you had to know how to do it for some reason. And some of these numbers, I think it was actually on the assignment, weren't some of the numbers quite large, like 59 or 60 something? Yeah, that was just because the student last semester. This says we have to have large prime numbers. I'm like, fine, here. I actually had them larger, but they were excessively large. So I shrunk them down some. Because I wrote a script to generate all these questions, too. I don't think I'll create it by hand, do you? Okay. Is everybody okay on how to calculate D?
I always assumed that Roy was the script you used to
I don't know.
generate a lot of.
Roy helps you with a lot of scripts, but normally they don't have to go fix it. But no, all these, I was sitting there one day, I'm like, make them really fast. So And I even made it so it actually generates the entire CSV, dumped it right into D2L, done. So, pretty nice. Okay, so summary. N is P times Q. Everybody okay with that? Which should be distinct prime numbers, but you're going to use whatever I tell you on this. Okay. The totient of N is actually P minus 1 times Q minus 1. Easy enough. E is less than N such that the greatest common denominator of E in the totient is equal to 1. Or in other words, use the one I give you. That's the easiest way there. Calculate D using the comparison method. Here's where it gets different. Let's look at those last two bullets. So I say M raised to E mod N gives us C. Then C raised to D mod N gives us M. Everybody okay with that? I just replace P with M. Normally it's P for plain text. This example is just P. It's just M instead of P, that's all. Because we're using P of, and I want anyone to get confused. So I knew that if I had a P there, someone would say, but wait a minute, so you mean P at the very... No, it's not the same P. Very simple to do. Any questions on RSA? Is that the easiest one yet? I guess Caesar cipher might have been a little bit easier, but not by much. And the funny thing is, this thing is so easy and is still used today. So why isn't this being used for everything? I explained it at the beginning of class.
Hardware failure.
No, not hardware failure. Before this, I explained it in the last lecture. What type of key is this? Symmetric or asymmetric?
Symmetric.
This is asymmetric. Public key encryption. Remember, there's two different keys. So it's asymmetric. Which one's faster? Symmetric is faster. 10,000 times faster. So the other one is used more because of the speed of it. This is asymmetric because we have an encryption key and a decryption key. I mean, look down here. We got M being raised to the E, C being raised to the D.
What's G?
Where's G? Oh, greatest common denominator. Divisor, I'm sorry. Greatest common divisor. Again, you don't need to know that because I give you E.
Okay.
I will always give you E. You have to calculate D. Okay? So yeah, this is asymmetric because there's two keys. This is, I think, the first asymmetric we did, isn't it? I think. Maybe. All right. Is that short and sweet or what?